All right, good afternoon, everybody, and good morning to somebody out there. Thanks for attending another one of our Thursday webinars. I think this is number 6, and I don't see us stopping anytime soon. So I hope everyone's enjoying it and that you're seeing some value here. Today we have Toth, who is one of our instructors. He's also with a company called Swiftshore Vessel Solutions up in Canada. Most of you, or some of you, may have had him for a class. I'm fortunate enough to have worked with them, and I'm fortunate enough to also call him a friend, so I'm pretty fortunate here with that. And he's going to go over some battery stuff for you. So he has a lot of experience with it, and hopefully you guys learn something good. So just going to go through some of the basics I cover every week. We're all still working from home. It's working well. We have our online classes. We're constantly evolving to try new things, including, I'll mention a little later, our learning management system, if any of you are doing our online classes. So constantly evolving. Everyone's working. Any tech questions you have, let us know. Membership, if you're not a member and you're curious, just let us know. We can give you some info on being a member, as well as our certification classes that are online too. We offer registration to our members first. So if you are a member, you get that email first, and then we open it up to everybody else. And as always, if you have a new topic, let me know. I'm trying to plan these things out as far as we can and want to make sure we're giving you what you want. CEUs, same as last week. So if you want to apply for your CEUs, tomorrow you're getting a follow-up email with a link. And if you're watching this on YouTube, you will get the link at the end of the video, little pop-up box. Any questions you have throughout this, enter them into the question box, and I'll be reading them off to Ray at the end of this presentation. And if you have any technical issues, I encourage you to log out, log back in, or try calling from your phone. That works pretty well. All right, cover a couple of our resources here. As always, we have our standard online cert, which is great. We have some discounts out there for that for some affiliations, so reach out if you have any questions on that. As always, I'm going to hit it again. We have our textbook for schools. Thanks again to AIM for partnering with us on this. And if you have any educators who could use that textbook, let us know. Also, you can visit teachquotes.org to sign up for a mail list on educational offerings for educators, rather. We have our self-proctoring, as always, which is a really great thing to take an exam at home. As far as the online learning goes, we have our free micro courses out there. We have a bunch of sales ending. So all those sales that came out in the beginning of April for our basic electrical, essentials of outboard service, they're all ending today. So if you're interested in those courses, take a look, and you can go ahead and purchase those. With that, we are pretty excited to announce that we have a new learning management system coming online. We've taken a lot of feedback from some of our courses. So it's going to be a really great system, enhanced capabilities for us. And I think all you guys are really going to like it if you use our online learning. So with that, the transition is happening tomorrow. So if you're currently taking a course, have any issues with it, there may be a little bit of hiccups for the next week or so. But you can email education@abycinc.org with any question you have or any issues. But just know your records might look a little funky, or some things might be a little different for the next week while we implement it. But in the end, it's going to be a really, really great program. Our online classes, I mentioned last week that we're scheduling more, and we already have another electrical on the calendar. So our systems, there's still some availability in that starting May 26th, and our electrical starts June 16th. And it's in a really great format. We take live questions. It's been working really well. So if you're looking or have been looking to take a certification course, go take a look at this and see if it's something for you. There's still availability in both of those classes. And lastly, before I turn it over to Ray, next week. So we have our topic set for next week, and I'm pretty excited about this one. So it's common mistakes in fiberglass repair. We have Jeff Wright, who's a VP of Technical Service at the Goujon Brothers, so Wet Systems. We're pretty excited there. And Richard Downs-Honey, who's the president of the Landing School, has a ton of composite experience. So it's going to be a little basic, and we might end up doing more of these with them because it's a really neat topic. So look out for the registration for that. And from here, I think I'm ready to turn it over to Ray. So Ray can do a little intro on himself. I'm going to drop my webcam here, and I'm going to give you controls.
All right, everybody. Well, I hope everything's going well with the social distancing, and let's jump right into this pretty soon here. Okay, so welcome to ABYC's batteries, the good, the bad, and the ugly, both selection and install. So again, I'm Raymond Toth, president of Swiftshore Vessel Solutions. I'm an ABYC Master Tech, NAM CMS surveyor, ABYC instructor, and NMMA engineering compliance specialist. So today we're going to beat up on batteries. Our next slide, a bit of an intro here. Okay, the creation of this presentation is provide the viewer with basic battery theory and installation practices based on ABYC standards. Okay, working around batteries and electrical systems is inherently dangerous. Always remember the proper use of proper protective equipment and safe operating procedures are required at all times. I'm going to give a big shout out to a couple people here. One of them is Nigel Calder for using his illustrations from the Boat Owner's Mechanical and Electrical Manual. Okay, and remember, ABYC is considered the industry accepted best practices. Remember, with battery installs, CFRs and all federal and statutes and laws and states apply. Now, I'm sure everybody like me, ever since this social distancing has started, we're starting to get a little bit punchy, and I can understand that. Myself, working alone most of the time, I tend to get a little punchier than others. So if you see me wandering around like this, you know exactly what's happened. Okay. It's just me having a staff meeting with myself. So today we're going to cover battery basics, the basic corrosion quadrangle, battery composition, different battery types or chemistries, unique characteristics and considerations of each, battery ratings, applications, and arrangements and installation. So this is going to go fairly quickly. Again, this is a very basic presentation, and most of it's going to be based on your typical wet acid flooded battery. Okay. So last week we were fortunate enough to have John Adey do Corrosion 101, the president of ABYC. And John, thank you very much. You did most of the heavy lifting for me coming into this lecture. Because as we learned last week, with corrosion, we have to have 4 elements. We have to have an anode, which is a metal that's more negative than the cathode. There has to be an electrical connection, and they have to be immersed in the same ocean or electrolyte. Okay, so you'll notice here, reviewing some of John's stuff, that we have our mild steel, okay, on the right-hand side of the screen, and it's connected by a wire to a piece of copper sitting in a beaker. Now, the mild steel, when compared to a silver-silver chloride reference cell, has a resting voltage of approximately minus 0.6 volts, okay, all the way up to minus 0.7 volts, okay? Whereas our copper, it is more positive. Its resting voltage when compared to that reference cell is minus 0.3 to minus 0.4. So what happens is we have created a galvanic couple, and now electron flow begins from the anode to the cathode. Okay, basically all that corrosion is Mother Nature's way of returning things to their natural state. Okay, so what's happening here is these two metals that are now connected are trying to polarize, and the electron flow is going from the more negative to the more positive. Really, that's all that happens in a battery as well. It's the exact same thing. We're actually using an electrochemical process to store energy and then release it or use it when we complete the circuit, okay? So here is our mild steel at minus 0.6 millivolts. And we go down to our copper over here. Can everybody see the cursor on the screen there? To minus 0.3. So that's basically what's happening there. So what we've done, or what the powers that be have done that decided to build batteries, is instead they use a lead anode, okay, connected by a wire, to lead dioxide, which is the cathode. And all it is immersed in a common electrolyte, in this case, sulfuric acid. So we have the electron flow going from the anode through the wire to the cathode, and the ion flow in the water completing the circuit. So now if we were to cut away a typical 12-volt battery, this is what it would look like inside, okay? what we have is the outer casing or the outer container. We've got our positive plates, which are lead dioxide, okay, and our negative plates that are lead. You can see they're connected up here by these metal tabs, okay? And there are several of them arranged in a cell. So you'll notice this battery has 6 cells. So basically, each cell, when it's fully charged and has rested for a day or two, has a resting voltage of 2.1 volts. So if we have 6 cells, we have a resting voltage of 12.6 volts. If it's a 6-volt battery, then obviously we have a resting voltage of 6.3. It's pretty simple, okay? So basically what we're doing is we're using corrosion to our advantage in order to store energy. Likewise, when we run the battery dead, basically we use an electrochemical process or type of corrosion to recharge the battery in the opposite direction. So the next slide actually shows you what the state of charge is, okay? So on the left, the column on the left-hand side goes up to 12.6 volts and down to 1.2 volts. On the bottom, horizontally, is what's considered the battery state of charge at that voltage. Now you'll notice an interesting thing. A fully charged battery is considered full or fully charged when it reads 12.6 volts. But you'll notice a dead battery is down near 11.6. Now, this is typical for a lead acid battery. Now, some batteries, some lead acid batteries have slightly different chemistries than others, and their zero state of charge may be considered slightly different. But this is important to remember, okay? A battery down to 50% state of charge is at 12.2 volts. And we're going to come back to this later because this is really important. Okay, right now we're going to talk about battery chemistry. You have your traditional flooded cell battery, and that's your typical battery that has removable tops. You can top it up with distilled water if some of the electrolyte boils out due to overcharging, okay, or evaporation, okay? Remember, these batteries have to be kept upright, and ventilation is extremely important. I mean, ventilation is important with all batteries, but extremely important with a flooded cell. The next is a sealed flooded cell, which is basically the same thing, except you don't have caps where you can access and top up the electrolyte. You see these in a lot of automotive applications. Your typical car battery has the sealed flooded cell type. Now, about 25, 30 years ago, gel cell batteries became quite the hit in the marine market. And they were popular because the electrolyte isn't a liquid, okay? It's actually a gel, okay? Now, gel cell batteries present their own limitations. They're very effective, but they're also very finicky, okay? If you don't have some form of charge regulation, what can happen is you can actually boil out the gel or dry them out. And because these batteries, just like AGM, sealed, they're all sealed batteries. So what happens is once the electrolyte leaves the battery, you can't put it back in. And eventually the battery fails, okay? Now, absorbed glass mat is a little bit different. Okay? Basically, these batteries have a fiberglass mat that's between the cells, and it supports the electrolyte, okay? Because of this, there's less internal resistance compared to a traditional flooded or gel cell battery that's using lead plates, okay? When you have less internal resistance, it means the battery can charge faster, okay? It has a faster charge acceptance rate, which means it can take more amperage. One thing to keep in mind is all of these batteries, okay, they have varying characteristics and varying needs and charging needs, and they have to be taken into account. Okay, when it comes to battery chemistries, okay, don't mix battery chemistries. Okay, several unfavorable results occur. The first and the most prominent is decreased battery life. Okay, undercharging, overcharging, it results in a poor customer experience. And when customers are not having a good time because they shut their boat off at anchor for 3 hours to go for a swim and are trying to get back to the marina and their batteries are dead. It's made for a rough weekend for them. The other thing you have to be very cognizant of is overheating and possible fire explosion. All of these batteries have different characteristics depending on their chemistry. And there's a saying in the boat building industry, and it's dead people don't buy boats. Okay, let's keep people safe. Let's make sure we know what we're doing. If you're in a situation where you are going to mix battery chemistry aboard a boat, like you're going to use wet cell for engine start and you're going to use AGM for a house bank, be very careful because those different battery chemistries require different charging voltages and regulation. So what can happen is when you mix chemistries aboard a boat is you can have one battery run dead, or it'll experience a much shorter life due to sulfation, which I'm going to cover later. So keep in mind, try to keep battery chemistries on board the boat the same so that you can use one battery charger as opposed to having two different chargers for each chemistry. So in order to understand what's really going on with batteries, we need to have a look and see how they like to be charged. We also need to see what happens to them internally. And I really like this chart. It explains a lot. So if we look on our left-hand side, the far left, the column on the far left starts at the baseline of 0% and goes up to 100%. And that's the percentage of amperage that's being put into the battery, okay? The next column beside it is voltage, okay? And our row on the bottom is expressed over time. So new electronic battery chargers, newer chargers, they're multi-stage chargers, okay? What that means is when the battery is getting near dead, or in this situation, you've gone out, you've used some appliances and you realize that the battery needs to be charged again. So we're sitting at 12 volts right now. And what happens is your charging source kicks on and it starts putting out voltage, okay? And typically the voltage will start, as it's putting voltage into the battery, the voltage starts to increase in the battery. That same charger will put out almost the maximum amount of amperage until it realizes that those plates are basically full. Now what happens is, at that time, the charger maintains the battery at between 14.2 and 14.4 volts, but you'll notice the amperage, the percentage of current being put in the battery drops off, okay? And the reason is those plates inside the battery can only absorb so much charge at a time. Once maximum absorption's been reached throughout the plate and you reach that threshold level, then up here, the voltage drops down to about 13.2 to 13.6 volts to handle some of the small typical loads. And you'll notice the amperage goes way down. And the reason why that is done is so that if the amperage was kept up at 100% or near 100% all the time, we would have a situation where we would be boiling electrolyte out of the batteries, okay? Now, this becomes more important, especially when we look at different battery types. Now, I've got to apologize for this slide. I don't know if this piece of paper went through the wash and then I decided to take a picture of it and put it up. I know it's a little tough to read, but if you notice, what we have here is the top chart is a typical wet acid battery. The next chart is a gelled electrolyte battery, and the third chart is an AGM battery down here. Now, the important takeaway from this is you'll notice the wet acid battery, or the your typical wet cell battery, okay, it can handle 14.2, 14.4, 14.6 volts when it's charging in the bulk and absorption phase. But if you go down to a gelled electrolyte battery, that's a whole different story. Because of its different characteristics and chemistry and internal resistance, it does not like the higher voltages. So your typical alternator, okay, that doesn't have an external regulator or isn't self-regulated, if you put gel cell batteries in a older boat that has a typical ferroresonant charger with a typical alternator, then what happens is you're putting too much voltage into the battery. And one of the worst things that can happen look like this. Okay, this is what happens when you don't have proper voltage regulation. It can lead to severe sulfation, overheating. You notice the top of these batteries. Okay, these are the vent, each cell is vented, but you can't pop the top off to change the electrolyte. Okay, so when these batteries boil, they vent, they discharge the hydrogen gases, and basically you end up boiling the battery. So this is a scenario where the boat owner was extremely lucky that there wasn't a fire or explosion. Okay, so we're going to switch from battery chemistry, and now we're going to talk more about battery types. And I like to break them down into two basic categories. You've got your cranking batteries, okay, and they're designed to deliver a high amperage of current for a short amount of time. Okay, they have thinner plates inside, which means they have less internal resistance, which means they can charge up much quicker compared to a deep cycle. And this is typical of, an automotive battery or engine start batteries. Okay, so they're designed to give a high current for a short duration application. So you'll see these used for engine starting, anchor windlasses, and sometimes bow thruster loads. Our other battery type is a deep cycle battery, and these batteries deliver a moderate charge over a longer time, okay? And they generally have a longer life cycle, but remember, they also take a lot longer to charge. And the reason is, if you take a look at, let's say, two group 27 wet cell batteries, one's a cranking battery and the other's a deep cycle battery. If you were to pick up the cranking battery and then pick up the deep cycle battery, you would find that the deep cycle battery weighs significantly more. And the reason is the thickness of the plates, okay? So deep cycle batteries are used for lower current applications over a longer duration. So house loads in a boat, navigation systems, electronics, nav lights, those sorts of things that are lower draw and are required over a longer time. And again, just remember the main difference between those two batteries is basically the thickness of the plates in each cell. So now we're going to get into battery sizes and group numbers. I really like this chart because it gives you the basic dimensions of the different types of batteries. Okay, so your small group 24 is usually used on smaller engines for engine starts. And then your group 27, it's usually used, it can be used for house or engine start loads, depending on whether it's a cranking or a house deep cycle load battery. Okay. A takeaway from this chart is you'll notice on the bottom, if you look at your group 27 battery, it says that it has a capacity of 100 amp hours and its cold cranking amps are between 550 and 800. So when we're talking about batteries, be very careful not to compare apples to bananas. When we go battery shopping, there are different ratings for batteries. Down here, these batteries in this chart are listed in cold cranking amps. And cold cranking amps are basically how many amps a battery can deliver for 30 seconds at 0 degrees Fahrenheit while maintaining proper voltage. Whereas marine cranking amps, okay, is what a battery can deliver for 30 seconds at 32 degrees Fahrenheit while maintaining proper voltage levels. So the big difference here is the 32 degrees Fahrenheit for a marine cranking battery compared to an automotive battery rated in cold cranking amps. So, and one of the reasons for this is, for the most part, especially in the recreational world, we're not worried about our batteries getting below 32 degrees Fahrenheit, because if they do, odds are that the water's frozen. Okay, we're not going to be out there playing in it. Now, the next big takeaway from this is, I get this question a lot actually, is what is the amp hour rating? Okay, so if we look at our Group 27 battery down here, it's rated for 100 amp hours. And what that means is how much current does that battery have over a 20-hour rate? So what they're saying is, if you've got 100 amp, if you've rated a battery for 100 amp hours, then the manufacturers basically tested it and they've pulled 5 amps out of it for 20 hours. Okay, so that's what amp hour capacity actually means. So before we get too deep on how we're going to use these batteries or how we're used to seeing them on boats, we're going to cover some very basic circuits. So this first circuit is a series circuit, okay, and it's quite simple. The total resistance in the circuit is the sum of the resistance values for each load in the circuit, okay, and basically the amperage draw in the circuit will be the same throughout. Now, our other type of circuit that we see on boats is our parallel circuit, okay? And basically what we're looking at here is the sum of the separate amperage draws equals the total circuit current draw. And that's pretty much the easy way to look at it. So if I were to relate this to batteries, okay, instead of basic electricity, we'd have two scenarios that look like this. On our diagram, we've got our parallel battery on the top, okay? And you notice the negatives are connected and the positives are connected. Whereas our series batteries on the bottom gives us something completely different. And the easy way to look at this is using a typical D-cell battery. If I have 4 D-cell batteries that get stacked in a flashlight, okay, they would be in series because it's positive, negative, positive, negative. What happens in this series, series circuit, is each battery has a voltage of 1.5 volts. Now let's say that each battery has 1 amp hour capacity. So what we get when we stack batteries or connect batteries in series is we get the sum of the voltages. So 1.5 times 4 is 6 volts, okay? But those 4 batteries are only going to last for 1 amp hour. Now, if we go down and we connect these in parallel, now we have something completely different. What we have is a total voltage of 1.5 volts. But what we've done is we've increased our amp hour capacity by 4. So we have less voltage, but they're going to last 4 times as long. Okay. So why do we combine batteries? Well, we combine batteries to prevent sulfation. And sulfation is basically a buildup of a crystalline structure that happens on the negative part of the battery, or the anode lead portion of the battery. Okay, so remember, a battery is considered dead when it's between 10.5 and 11.6 volts, not when it's at 0 volts. Okay, at 11.6 volts, almost everything aboard your boat will almost cease to function. Lights will be extremely dim. Small motor loads will barely turn. Okay. Remember, the resting voltage of the battery should be 12.6 volts. Okay. Now, a lot of battery manufacturers say it's accepted good practice to start charging the batteries when they reach 12.5 volts. I mean, that's only a difference of 0.1 volt, which isn't very much. Okay. Now here, the interesting takeaway from this is good marine batteries are rated by their cycles, how many cycles a battery can go through. And so 1 battery cycle, okay, most manufacturers consider it drawing down a wet cell battery from 12.6 down to 12.3 volts. Okay, that's 1 cycle. So if you've got a battery that's rated for 2,000 cycles, they're only considering a difference of voltage of anywhere between 0.1 and 0.3 volts from fully charged to when you should start hitting it again. Okay, so like I said, batteries are rated for the number of cycles they can perform before they fail. So that's one of the reasons why we parallel configurations of batteries for house loads in boats, is because our amp hour capacity increasing reduces the number of cycles that a battery has to go through, okay? And therefore it extends its life. You'll see it in a lot of boats that are, you know, smaller boats that are, you know, anywhere between the 20 and 30-foot range, where space is limited and people are starting to use them for extended periods of time, and they're noticing that their house bank is going dead very quickly. And the reason is, a lot of times, is they just don't have the amp hour capacity. They don't have the physical room to put in 2 or 3 Group 27s. And therefore they're asking too much out of their battery and it fails prematurely. Okay, so as I said, sulfation is the process that builds up on the battery cell negative plates. And like John 80 covered in Corrosion 101 last week, when that happens, when you start to take away from the surface area of the anode and the cathode, then they become less effective. So the same thing happens inside a battery, and it's caused by persistent undercharging or excessive discharging. Okay, so as I said earlier, a multi-modern stage battery charger, they have their float stage, their equalization stage, okay, and their bulk stage. But the newer chargers also have a sulfation stage, and sometimes they call it equalization. And what it does is it basically throws in a little more voltage. Instead of putting in 2.3 volts per cell, it'll pump it up to 2.5 to 2.6 at a very low amperage. And what that does is that gets rid of the crystalline buildup on the outside of the plate structure. Here's where the rubber hits the road. I love this chart. And on the left-hand side is the number of cycles until a battery fails. And on the bottom is the percentage of discharge for each cycle. Now you'll notice, if you've got a large boat with a massive battery bank and you're meeting all your charging needs and you're not pulling down on the battery significantly, look at how many cycles that we can get out of this, you know, up into the thousands, okay? But look what happens once we start getting past the 15%, 20%, the curve starts dropping very rapidly. And what happens is you start dropping off into, you know, eventually 200-300 cycles. So some of the smaller boats that are pulling their batteries down to 12, 11 volts, that's why the owners are having to replace their batteries, you know, annually or once every 2 years, is because they're just not, they don't have enough amp hour capacity, or the load calculations that have been done, there's just too much draw for the storage capacity for the batteries that's on the boat. Okay. So next we're going to get into some more hands-on stuff and get away from the theory. Okay. This is some of the stuff out of ABYC standards, and it's really important that everybody understands this. You know, connections that you make to batteries, they have to be made with secure mechanical fastenings. I go on boats all the time and I see someone is using the alligator clips from a battery charger and they just clamp them on the top of the posts and walk away. Okay. Anything that uses spring tension is forbidden. Okay. Using wing nuts to secure battery cables to a post. Okay. Marine battery manufacturers generally include the wing nuts for smaller items, smaller low draw items. Okay. And the standard states that any conductor that's 6 gauge or larger is not allowed to use wing nuts for connection to a battery. Okay, this is a big one. When your battery cable connections, when your main feeder cables, you know, there's a lot of amperage going through there. And when they get loose, when they get corroded, when they get damaged, anytime you have resistance in an electrical circuit, the result is heat. Okay, and heat can cause fires. So this is nothing to mess with. Okay, another one you see all the time is batteries need to be secured to allow less than 1 inch of movement, okay, in any plane. So basically, it's less than 1 inch of movement over 1 minute, with being pulled twice the battery's weight or 90 pounds, whichever is more. And another one that's overlooked is proper venting of batteries. Okay, make sure that these are properly vented. Even the sealed batteries, remember there's a regulating valve on them, and if they become overcharged, then what's going to happen is they're still going to vent, and they do that so they don't explode. But those batteries, they're venting corrosive hydrogen gas, okay, and it can be quite explosive. So we don't want to install batteries or install our battery charger directly above, or our charger inverter directly above that those batteries, because if they vent or if they start to gas, then those gases are extremely corrosive. Okay, we talked about combining batteries. The big one is never combine batteries for different vintages or different types. So if you've got a boat and it's using all gel cell, fine, but make sure you've got the proper charge regulation from the alternator and the battery charger is on the correct setting. Okay, likewise for flooded cells or AGMs. Also, a strong battery will tend to discharge into a weak. So if you think back to the very first slide I put up, where we had the anode that was more negative wanting its electrons to move to the cathode, this is basically what happens in a battery when you get a dead cell or a weak cell. It will pull down the other cells, okay? So when I replace batteries on my own boat, if I replace one battery, I replace them all. Now, here's a nice little diagram out of E11. And I really like it because it has your typical battery charger, or sorry, this is out of A31. But this is your typical battery charger install. And you'll notice how it shows you where the overcurrent protection should be and how it should be connected, okay? Battery chargers are nothing to play with. They need to be hooked up correctly. And unfortunately, either because people get in a rush or they're just not sure how things should be done, you can sometimes run into situations like this. Now, there's a lot of standards-based issues that are incorrect with this install. We could talk about the greater than 1 inch of movement that's allowed. We could talk about the wing nuts that are used to hold on these feeder conductors that are larger than 6 gauge. We can talk about how the positive boots aren't covered with a protective guard to guard against shorting. And if somebody isn't sure what the definition of cold cranking amp is, then just take a wrench or a screwdriver and short it out between the positive and negative terminal. You will have a smoke show like crazy. It's really important to keep these positive terminations covered, okay? Another standard-based issue is over here. You'll see on the bottom right battery, on the positive post, we've got more than 4 conductors. Also, the conductors aren't stacked properly. The largest termination needs to go at the bottom and the smallest gauge termination at the top. On to another one. This one's really important. I found this install in a gasoline-powered motor yacht. And you can't see it in the photo, but up near the top back here, there's a big hole drilled through into the engine compartment. So basically everything was thrown in this battery box, homemade battery box. You'll notice the bottom's made of wood. And the standard clearly states that battery trays or boxes need to be constructed of materials that will not be susceptible to electrolyte attack, okay? So you'll notice this isn't a great install. So what's scarier with this, this picture, you'll notice over here, there's a 120 volt receptacle inside the battery compartment. And scarier yet is this jug on the right, which was actually acetone and was about, I don't know, a quarter full. We had a very dangerous situation here. And obviously there were a lot of issues going on. One of them being ignition protection, since it's exposed to the gasoline fuel space. Using battery boxes for storage of items. Everybody understands that space is limited on a boat, but do not store anything that is not part of the battery install in the battery box. Here we have an example. This was an older steel boat, but you can see they were, not only did they mix battery chemistries, but they were also using these type alligator spring type connections to charge their batteries. This was an install. Now this is on a 30-foot sailboat, and the client didn't want to be bothered running the conductors all the way back to the DC panel. So he took this battery and put it up in the locker in the V-berth. So this is sitting on the top locker in a shelf in the V-berth. No overcurrent protection. There's a host of things wrong with this photo, and it's generally not good. Another reason why batteries become neglected is sometimes because of their location due to the design. Now, the photo looks pretty simple off the start. I mean, you can tell that this battery's been neglected, and you can see that, obviously it hasn't been serviced in a long time. It's in rough shape, okay? But if you look closer at the photo, this is in a 36-foot sailboat, and it's a early 90s sailboat. And in order to get to this 8D battery, I physically had, in the cockpit, I had to climb in the port side locker, down past the battery charger. I'm actually in at the stern of the boat. And if you look at the bottom left of the picture, you can actually see the gland for the rudder post, okay? So I physically had to climb down in and around a corner to get to this battery. So the owners had not serviced it, not maintained it, because literally it was all I could do to climb in there and just open the enclosure for the battery that far. So in conclusion, remember, a weak battery cell will bring down the remaining cells in that entire bank, not just its own battery, but the entire bank. Takeaway from this is a battery resting charge voltage is typically 12.6 volts. Never mix battery chemistries, okay? Different chemistries require different charging sources. Use deep cycle for house loads and cranking batteries for high amperage applications. And always install the batteries according to the manufacturer's recommendations and ABYC standards and CFR requirements, or Transport Canada requirements. All right, so thank you very much for joining us. I'd like to thank John Adey, the whole crew at ABYC, David, everyone for allowing this to happen. It's a great way during all this social distancing and isolation and stuff for us to kind of keep our head in the game. And it looks like we do have brighter days on the horizon. So you can obviously pick up this feed at abycinc.org, ABYC's YouTube channel, or at swiftsure.ca. And I don't know how everybody else is feeling, but I'm pretty sure we made it.
Yeah, thank you very much, Ray. And we do have some questions piling in here. Before we get to them, as we do every week, I want to send out a quick poll question. So anyone who gets this right will be entered to win a prize from us, a hat or a T-shirt. So with that, I'm going to launch this now, and you're going to see it on your screen, and everyone has a chance to guess. So let me just pull this up. All right. So, Ray, we had a 88% correct rate on 32 degrees Fahrenheit.
Nice.
So
That's
people
good.
are paying attention. So we got about 10 minutes or so, Ray. So I'm going to start firing some questions off at you if you're okay with that.
Absolutely. I'll give it my best shot.
All right. And any questions that Ray doesn't get a chance to answer after this, you could shoot me an email. I can get our tech guys on it, and we can gladly get anything answered for you. So first question, when a vessel sinks in salt water and the positive battery cable burns off the post, is this considered electrolytic corrosion? Does the electric charge enter into the water and discolor metals, or is there a galvanic or electrolytic situation?
There's actually a lot of things going on. So just so I understand correctly, the vessel sunk?
That is what it says here, when a vessel sinks in salt water.
Right. Okay. Well, actually, a similar thing can happen in freshwater as well. So what you have going on is you have two things going on. You have the galvanic corrosion, but definitely straight current electrolytic corrosion, because now the ions in the salt water are creating an unintentional path between the positive and negative battery post. Okay, so now we have a completed circuit, an unwanted completed circuit, and if the ion concentration is high enough, it can actually happen. And I've actually seen similar situations in freshwater as well. This isn't common to just salt water. If a boat goes down, generally there's enough ions in freshwater to also be the charge carriers and complete that circuit.
All right, next question. Is there a reason not to use golf type batteries instead of 4D?
Generally, it depends on the battery manufacturer. And if you remember the slide I had that had the internal components to a battery, basically between each negative lead plate and lead and positive lead plate, there's electrical sleeves or insulators. Okay, and what happens is, depending on the thickness and the robustness of those insulators, depends on, really tells you how much damage and abuse a battery can take. If you take a boat, and you're coming off a wave and you hit bottom, you could have 3, 4, 5 Gs subjected on the internal components of that battery when it hits the bottom of the wave. That's an excessive amount of force. So a lot of times it will depend on the manufacturer and the quality of the case and the separators and insulators within the battery itself.
All right. Next question. How close can the battery be to an above deck gas fuel tank plastic?
The standard says that the topmost posts, there is required to be a dielectric shield above the positive and negative post of 12 inches, and that's for any metal components. Now, you're talking about a polyfuel tank, which is non-conductive. Now, I would still go with the old rule of 12 inches, even though the tank isn't metallic. And the reason is just for sheer safety.
Right. If you have an ignition protected battery charger, do you still have the same fire risk if the charger is mounted above the battery?
Well, what we concern ourselves with an ignition protected component, so obviously we're dealing with a gasoline fuel space with this ignition protected charger. The reason why we don't want to mount the charger above the batteries is because of the corrosive hydrogen gases. When they start to break down the components of the charger, it is no longer considered ignition protected. Now you do have the possibility of sparking and other severe reactions. So the simple rule is never mount an ignition protected charger or any electronic device directly above batteries without an intervening barrier.
All right. Next question, which you may or may not know. I don't know this one, but those electrical committees, they do some interesting stuff. So is the restriction on wing nuts because they can't be tightened sufficiently by hand?
Yes, that's the short version. That's the short answer. Basically, there's no way of being able to torque them down properly. Most battery manufacturers recommend a torque spec, for the 5/8 and 1/4 inch nuts or for their posts. They have torque specs for all their battery posts, and a torque wrench should be used. We have no idea of knowing what kind of force is being put on that termination on that battery post if we're using a wing nut.
All right. For long-term storage, is it better to have a battery switch turned off or with a smart charger with trickle charge?
There's a couple factors. First, it would depend on which switch you're talking about. Are you talking about, let me just clarify and try and knock it down first. The battery isolator switch between the battery and the rest of the systems, if you're going to store the boat, should generally be in the off position. Now, on the AC side, if you have a battery charger that's a multi-stage battery charger that is capable of also the equalization and sulfation float charges, if you can, then there's nothing wrong with leaving that charger plugged in.
All right. Just getting through some of these questions here. How many batteries maximum in parallel is advisable for 24-volt boat domestic system? Does it depend on the brand or the amp capacity?
Can you ask that question again, please, David?
Sure. How many batteries maximum is in parallel is advisable for 24-volt boat domestic system? Does it depend on the brand or the amp capacity?
That's actually a tricky question. Depending on the size of the vessel, remember, the more batteries you have on board in a parallel or series parallel configuration, the greater your amp hour capacity is going to be. Now, the problem with that is having a charger that's large enough to adequately charge a bank of that size. And that's where the real trade-off comes in. So you're going to have to look at what the amp hour capacity rating is by the manufacturer for each battery, but you're also going to have to look at the ability of your charging source.
Got a ton of questions here, so I'm trying to grab some that we can answer.
All right, let them rip.
Yeah. So this will be our last question here. And if you are replacing a large battery bank, how important is it to get batteries close in serial number?
To be quite honest, I think a lot of that depends on the quality of the battery. It depends on the battery manufacturer. Ideally, you would like to, because then you're dealing with batteries of similar vintage, which is always nice to know. That being said, if it's a good battery, a reputable battery manufacturer, then they're going to really let you know. They'll have a decent warranty as well. So if you do happen to get something that's out of date, they should stand behind their product. Oh, I can't hear you. I think you went.
Correct. Oh. Thanks so much again for presenting today. I know everyone really enjoyed this. We got a bunch of comments already. To address a couple things that I got in questions of, if you're looking for a certification class, we are doing some online. Look at our calendar. We don't really have any scheduled in person just because we don't know when this is going to be over. And also lithium ion. big topic. We're going to work to have its own day for lithium ion on one of these Thursday presentations. So if you're looking for your CEUs, you'll get an email if you're watching this live tomorrow. If you're watching on YouTube, a link should pop up somewhere. Matt always puts it in a different place every day to mess with me, but you will see a link to click on. And thank you again for attending. Any questions you have, please let us know. I can send your note to the tech guys or whatever we got if you have questions about this stuff. And if you've never taken a class with Ray, you might see him one of these days instructing for us. So thanks again so much, Ray. Thanks everyone for attending, and we will see you all next week.
Thank you, everybody. Have a great week.